Welcome everyone to the third DataFusion Community Showcase. I'm Wyatt with Spice AI, joined by my co-host Andrew Lamb of Influx Data. Great session today. Super excited to welcome Milind and Yaroslav. Milind will be kicking us off with a presentation on ASAPQuery, followed by Yaroslav presenting his project, Streamling. So yeah, just a few housekeeping notes. Please stay muted, of course. Feel free to enter questions into the chat as the presentations are going on. And then at the conclusion of the presentation, feel free to unmute and ask your question. Otherwise, I'm happy, or Andrew will be happy to ask those questions on your behalf. And I think that's it. Andrew, anything I'm missing?
No, this is going to be great. I can't wait to hear about all the cool stuff that's happening.
Cool. All right, Milind, take it away.
Yeah, awesome. All right. So, hey everyone, I'm Milind, and I'm going to be talking about ASAPQuery today, which is a drop-in query accelerator that we're building using some cool mathematical algorithmic techniques that I will introduce during my talk. And this is some of the, it's an open source query accelerator that's been born out of some of the research that I've been doing at Carnegie Mellon. We started building this for metrics observability as a use case, but since then we've been working on expanding it to other kinds of use cases and domains like general time series analytics. Cool. So I'm a PhD student at Carnegie Mellon, and I lead this effort called Project ASAP, which is a collaboration between Carnegie Mellon and University of Maryland. And the vision here is to take a bunch of cool, powerful yet sophisticated techniques from CS theory and CS algorithms and essentially use them to design like the next generation of efficient data processing pipelines. And we've been, across Project ASAP, we've been doing this for like observability, network monitoring, security, and beyond. So quick overview of the structure of this talk. I'm going to talk about what ASAPQuery is, and then talk about the secret sauce of where ASAPQuery gets its benefits from, which are these things called sketches. I'm going to give like an intuition about those and their capabilities. And then I'm going to talk about how we've been using DataFusion to essentially enable or democratize the benefits of these sketches inside ASAPQuery, and then some closing thoughts at the end. All right. So just I think a lot of people here might be aware of this, but this is what, let's say, a traditional metrics observability stack might look like. So you have some kind of, exporters on the left-hand side, which are, measuring your CPU usage, system level metrics, and they're sending it into, a metrics observability database such as Prometheus. And then you have a dashboard like Grafana that's regularly querying Prometheus and then showing you the results, right? So high level overview. So ASAPQuery is an accelerator that you can drop in to your existing stack. It sits between, the dashboard like Grafana and the database like Prometheus. And it essentially plugs into this stack using the remote write API. So I don't want to get into the details here, but essentially ASAPQuery needs the same raw data that Prometheus is getting, and that's one way that we essentially plumb the same data that Prometheus is getting to ASAPQuery. So I want to quickly, before I actually get into the details here, I actually want to show you what a before and after picture would look like, if you just have a traditional metrics observability stack versus one with ASAPQuery. What's the difference that you notice in Grafana? So this is like a Grafana dashboard that's running on Prometheus. You have some very high cardinality, high throughput data coming in. And every time the dashboard is refreshing, you see sort of this lag where Prometheus has very high query latency and it's trying to answer the queries, and it takes a few seconds. And you can have a different world after ASAPQuery, which is this world. So what I want people on the call to do for a few seconds is just to laser focus on this refresh button that you see on the top right-hand side, just for a few seconds. And you see, so that's how quick it was, right? So that's sort of the orders of magnitude latency difference that you get before and after ASAPQuery, right? That's basically what it enables. So much faster dashboards, and it's also able to reduce the CPU and the memory cost that actually goes into executing the queries. So what's essentially enabling all of these latency benefits and the cost benefits? And the answer to that is something called sketches or sketch-based summaries. Now, what I want to do right now is give you all like a quick intuition of what these sketch summaries are. And to do that, we are gonna forget about data and metrics and Prometheus and DataFusion for a second. And let's say you're on a Safari, right? So you're on a Safari. It's a 3-hour long Safari. You see a bunch of different animals as you're going on your Safari. And then at the end, your friend who didn't come along with you asks you, "Oh, did you see a giraffe on your Safari?" Right? And there's so many different animals. It's actually very hard to keep track of each and every animal that you saw. So keeping track of each and every animal is sort of akin to exact data computation. It gives you the correct answer, but it's very hard or expensive to do because you just cannot retain so many animals in your head. So the next best thing that you can do is you can sample. So you can say, okay, I'm not going to keep track of each and every animal that I saw. I am only going to keep track of every 5th animal that I saw. Okay, you could do that. It's sort of easy to do, but then you might miss rare animals, right? And so your accuracy can sometimes suffer. And so the third approach is essentially using these sketch summaries. So in this case, what you can do is keep this compact data structure with, where each, like think of it like a 1D array with just binary counters. And every time you see an animal, you hash it into one of those cells and you just keep like a yes or no for each of those cells. So this is sort of like a compact summary that you can build on top of your data. And this helps you answer, oh, did you actually see an animal or not? And this is essentially what is a sketch. So the sketch that I just described here is called a Bloom filter sketch. And this is a sketch which answers the query, oh, did I actually see an animal or not? Did I actually see an item in my data stream or not? But there are other kinds of algorithms that help you answer other kinds of questions. So another popular one is something called a countman sketch, which is going to tell you how many times did you see a particular animal. You can also, attach a heap to this countman sketch and answer heavy hitter kind of queries, which are like, what are the top 5 animals that you saw, right? So each of these different queries that you might want to ask, there are specialized specialized sketches that can help you answer these queries. So yeah, enough. So now you can take the same concepts that you applied to sort of the world of animals to metrics or time series data, right? So let's say if I have a metric like CPU usage, I can use the same techniques to answer different kinds of queries that one might ask of Prometheus, right? Is a particular host up or not? What is my average CPU usage? I can ask quantiles like P50 and P90 CPU usage, etc. Right? So that's basically the intuition of how these sketches are useful for these kinds of queries and analytics. Now, there's 5 reasons that I want to tell you here about why you would want to use these algorithms. So the first one is that they consume orders of magnitude lower memory than raw data, right? So if I have like gigabytes of raw data or terabytes of raw data, I can create sketches that are a megabyte or sometimes even a few kilobytes that are going to give me extremely accurate answers to each of those queries that I showed you on the previous slide. Right. So each sketch is sort of purpose built for a specific type of query. And so it only needs to retain some information about the data, which is where you're essentially able to get these massive benefits in terms of compression. The second awesome thing is that they can work with streaming data. So, you have like high throughput streams of data. You don't need to keep all of it in memory to actually compute these sketches. You can just stream the data in. The third one is that sketches as a data structure are mergeable, which enables you to do some cool stuff like distributed computation. So let's say I have two hosts that are completely separated out, and I want to analyze the data that is being produced from those two hosts. So the usual thing that I would do is I would stream the data from host 1 and host 2, let's say to host 3, where Prometheus is being deployed. But that requires me to send all of that data to a central host and then compute on it. Instead, with sketches, what I could do is compute a sketch on host 1, compute a sketch on host 2, and just send these light sketches to host 3, which can then merge them into a single sketch, which essentially represents all the data that you have seen on the two hosts. And there's some, the math behind these sketches is built in a way that they're essentially mergeable. There's some cool things, other cool things that you can do here, which is that you can actually compute a sketch on some data and then use that sketch for multiple different kinds of queries later on. So you essentially have this paradigm of compute now and query later, which gives you more flexibility with how you want to use these. And then you can actually tune the parameters of the sketch to get different cost and accuracy trade-offs here. So more memory, you can assign it more memory and essentially get more accuracy out of the sketch. So there's all these awesome reasons to use it, but the practical reality is they're actually extremely hard to use, right? And there's a few different reasons why. One is, and this is sort of the major one here, is that it's unclear how do you take a SQL expression, which has different kinds of constructs inside it, so aggregates, joins, filters, maybe time series operations. And how do you map that high-level declarative query down to these lower-level algorithmic primitives, right? That's kind of an unsolved problem here. And the other thing is that tuning the sketch sort of gives you a flexibility in saying that, okay, I can assign it more memory and just get more accuracy. But it also makes it harder to tune because then the onus falls on the user to say, okay, I want a sketch with these number of rows and these number of columns, or with a specific configuration or parameters. And sort of to add insult to injury, the actual error or the actual accuracy that you get out of a sketch depends not only on how you configure it, but the distribution of the data that you feed inside it. So this sort of just makes the problem more complicated. And so our aim here with ASAPQuery was, okay, can we democratize the benefits of these powerful but hard to use techniques for the world of metrics observability? And that's essentially what ASAPQuery is trying to do. All right, so now comes, so I didn't talk about Datafusion until now. Now we're going to get into Datafusion with that background here. So just sort of a quick, I guess, caveat that I wanted to mention here is that we built version 1 of ASAPQuery without Datafusion. And then we realized that some of the query planning and the query execution part would be helpful if we actually use Datafusion for it. And that's what I'm going to describe now. And then there are actually some questions that have come up as we've been doing that. And it's possible that we might move away from Datafusion in the long term. We might not. I'm honestly not sure. There are some questions that we're trying to figure out answers to. And I will actually have them at the end. And if people on the call have thoughts on that, that would actually be super helpful for me. All right. So essentially what you want to do is you want to take some high-level expression in SQL, someone writes a query, and you want to map it down to these sketch-based primitives, right? These algorithmic primitives. And at a high level, there are 3 steps involved here. So you can take a SQL query and convert it to a logical plan with Datafusion, but then this logical plan only has operators or operations from the world of relational algebra, right? So I can select something, I can project, I can filter, aggregate, etc. But now we need to represent sketch-based operations. So that's the first thing that we need to introduce. And then what we actually want to do is, instead of the user writing a query, which actually uses sketches explicitly, we just want to take their unmodified SQL and convert it to a logical plan that is able to leverage these sketch-based operations, right? And the reason is that, sort of in the spirit of SQL being a declarative interface or a declarative language, the user should just specify what they want to achieve or what they want out of the data. And the system should be able to automatically figure out, okay, if sketches are legal to use, what is the best way to use them, right? The onus should not fall on the user to understand what sketches are, how to use them, etc., etc. And so you want to automatically convert the SQL to sketch-based logical plans. And then you convert those, logical plans to physical plans, and then you execute them. And so, we've been sort of working on this process, and I'm going to describe each of those steps. But our ultimate hope here is, can we actually build, an algebra out of these sketch-based primitives, similar to how you have relational algebra, which is based on relations in the standard SQL world. All right. So here are some of the logical operations that we actually implemented with DataFusion. So I've called them summary here and not sketches, because actually, sketches are a particular kind of summaries, but you can use them for other kinds of summaries in general. So you essentially have one operator, which is a summary insert, which is basically the input is a set of data that I have, or a set of rows in a certain table, and the output is this sketch object. So that's a new operator that we added. And then we have the merge operation, which is going to take two sketches and then merge them into another sketch. The sort of complementary to this operator is the summary subtract operator. So think of it like a set intersection, where you take one sketch and then you have another sketch and you subtract the second one from the first. And by the way, the boxes here are sort of representing the data that the sketch is computed on. And then, given a sketch, you can have this summary infer or summary estimate operator, which actually then gives you, an estimate of a statistic of the raw data that it was computed on. So if I have these 5 blue boxes over here, I put them inside a sketch, and then I can use this sketch to infer, okay, what was the median of this data that was fed in? And then we added 2 more operators, summary read and summary write, which are sort of representing reading and writing these data structures to disk. One thing I want to mention here is that to sort of represent the schema of this summary data type, we just kind of hacked it and represented as like a binary column or a binary blob right now. We've been trying to think if we can up-level this as a first-class, data type, but I will, come to that in a few slides. So once you've defined these operations, what we want to do is actually use them and create logical plans here. And so there's sort of 3 steps here. So the first is you take an existing, logical plan that you would get from DataFusion, and then you try to find a part or subtree of that query plan that you can replace with sketch-based operations, or something that is sketchable, right? So that's basically one step that we do. And then the second step is we replace this subtree of a query plan, which is using only SQL operations, and then we modify the query plan to actually use the summary operations that I just defined on the previous slide. And the key to currently, we as experts of sketches have been defining what portions of a query plan are sketchable and what candidate, subtrees that we could replace them with. But ultimately, I sort of hope that through this process, we're able to, like develop this theory around like a mathematical theory which grounds this, similar to how relational algebra sort of grounds the world of SQL. So that's basically what we do right now. So we find a subtree that is sketchable, we replace it with these sketch-based operations, and then we actually get a bunch of different candidate plans, and then we try to choose a best sketch-based logical plan, which is currently based on some pretty simple heuristics. That's what's happening. And once we get this sketch-based logical plan, I think converting it to a physical plan is relatively straightforward right now. So we use like the extension planner hook inside DataFusion, sort of downcast each of these logical nodes to these summary operators, build a physical plan, and then we have our own library of sketching algorithms that we plug into this physical plan, and then are able to execute this and give you a result. So this is what is happening at a high level. So we defined sketch-based operators. We modified the usual SQL logical plan, and we manipulated to actually use these sketch-based operators. And then we convert that to a physical plan and execute it. This is what's happening at a high level inside ASAPQuery. Cool. So I'm going to try and end in 1 minute here. So there's sort of two things that we are trying to figure out, which goes back to my point that I was making earlier about some things that we're unsure about with respect to data fusion. So one crucial thing about sketches is that I can compute a sketch once on a data and then use it for multiple different queries that I can execute. Or I can use it for multiple different clauses inside a single query. And if you logically think about the query plan here, it leads to a structure where the sketch node can have multiple different parents inside DataFusion. And my understanding is that DataFusion as a framework does not allow it, but I think this is something that I'm trying to figure out, and I would actually love feedback on this, or someone tells me I'm wrong and this is possible, that would be awesome. But this is one thing that we're trying to figure out, if we can represent these kinds of plans inside DataFusion. And the other thing that I wanted to mention is that, like instead of representing sketches as this binary type, can we up level it to a first class, arrow type, and what would that take? And that sort of led to the question about what would columnar storage look like for these sketches or for these summaries, right? So if it's raw data, it's clear what columnar storage is. I have a bunch of rows in my table and I store them column by column. But then when you have these summary blobs, what does columnar storage even mean? I'm honestly not sure what the answer to that question is. So this is something that we're trying to figure out over here. So quick recap. So sketches are extremely powerful but hard to use techniques. And we've been trying to build ASAPQuery using DataFusion to essentially democratize the benefits of sketches. We start with metrics observability, but we've been trying to sort of extend it to other kinds of domains and use cases. And that is basically it. Awesome. Thank you. I would love to answer any kinds of questions, comments, concerns about what I talked about.
That is great, Milind. I don't see any questions we have in the chat, but I have several tickets I'll point you at about sharing inputs and stuff,
Okay.
which would be great, but I don't want to take that up in this forum. But thank you. It's great to see.
Okay.
Does anyone else on the call have things they'd like to ask?
Oh yeah, so I had a question. Can you go back to the second or the first problem you had with the multiple outputs? I'm just
Sorry, which one?
the slide you just had just before. Yeah, this one.
Yep.
And maybe I just didn't hear you right. So can you just explain again the problem that you have in DataFusion now? Like for me, at least from the diagrams, it's like I have two different queries at say two different points in time.
So there are two things that we're trying to figure out and they're related. One of them is that if I have a single query, and if I have a query plan, let's say logical query plan for that, my understanding is that each node in that logical plan can only have one parent. So the output of that node only goes to the input of another node. Now, to fully leverage the benefits of sketches, what I want to be able to do is actually take the output of this sketch node and have multiple parents that I can propagate that output to. I think that's not possible in DataFusion, but that's sort of one thing that I'm trying to figure out.
Right. And the need for that is related to sketches or related to
It's related to the
something
fact that once I have computed the sketch-based summary, I can actually use it for multiple different things downstream. So if I only use it for one parent node,
it's
I'm
just
not
less
able to
efficient
fully, yeah, I'm not able to fully leverage the benefits. And sort of the related thing, which is, maybe broader scope here, is that I think in most databases, and I think DataFusion as well, like query planning is done at a per query level, right? So if I get one query, I'm going to compute a plan for it. I get another query, I'm going to compute a plan for it. But let's say, if I know someone's going to send me a batch of queries together, which often happens with dashboards and stuff, can I compute a plan for that set of queries together as opposed to at a per query level? And the reason I would say this is because you can often reuse parts of computations that have been done across different queries. So
Right.
two queries are looking at the same filter. I can actually just do that once and then feed it to both queries. And this is not specific to sketches, but when you actually use sketches, there's more computation that can be deduplicated across queries, if that makes sense.
Yeah, exactly. No, the only thing is, so we've done a little bit of work on indexes, and not this exact problem, but this idea of that you have something that like has state external to the query plan that kind of influences how you do like whatever operations.
Yeah.
But when I was looking at the diagram, it wasn't exactly clear.
Yeah, sorry, I didn't.
But the diagram is about what you said in the second part, where you have these batches.
Yes.
And you can get a whole bunch of efficiencies if you're allowed to operate on N batches and not just one single query.
Correct. Yeah.
Awesome. No, really interesting. I just wanted to make sure I kind of grasp what this was.
Gotcha. Sounds good. Any other questions that I can answer?
Cool.
Okay, cool. Awesome. Thank you.
Good work, Milind. And if you wouldn't mind throwing your contact info into the chat, maybe folks would like to follow up independently as well.
Yes, thank you. I will do that.
Nice. Awesome. Yaroslav, take it away.
All right. I hope you can see my slides right now.
Yes.
Perfect. All right, so thanks everyone for joining. My name is Yaroslav, and just a few words about myself. I'm a software engineer. I've been working primarily with data streaming systems for the past decade or so. Recently, I launched a company called Iron Tools, and I'm doing data streaming consulting. Also a big fan of Arrow and DataFusion. That's why I'm here. And so today I want to present this project called Streamling. This is a project that was open sourced a few months ago. It's open sourced by a company called Gold Sky, so I used to work there. And this project is essentially a streaming runtime. So Rust, Arrow, DataFusion, all the familiar technologies. And we built a streaming engine out of it. So here on the right, you can see a very simple definition, like a YAML pipeline, where you can combine a streaming Kafka source, a SQL transformation, and a Postgres sink or destination. And you feed this YAML to a Streamling binary, and it just runs this pipeline continuously. The data is flowing through the system. So pretty kind of standard streaming setup. The engine comes with a few existing connectors. So there are like a few different types of sources, different types of transformations, quite a few sinks. And it's very easy to add new ones because we offer a very, very simple kind of plugin API. So you can build a plugin on the site, compile it, and then dynamically load it with the runtime. Very easy process. Now, you may ask, why build another tool? Because you probably already seen, streaming tools or engines, data processing engines like this, where you have a kind of declarative definition of your pipeline, and then you move data. So why build another tool? And when I just joined Gold Sky, we built a fully managed data streaming platform on top of Apache Flink. And that was relatively successful. So we had like thousands of pipelines in production. But when you use something like Flink, you're paying that big data price because Flink was designed as a large scale-out system. And so even though you can deploy it in a small scale, there is a fixed overhead. For example, each pipeline needs to have a special job manager component, which is wasting your resources, and you can justify the cost of that if you have like 2,000 workers. But you have two, and you always need to keep around some additional machinery at scale. And I'm talking about like thousands of pipelines. You will notice that you essentially wasting all the resources. And so I'm not saying Flink is inefficient. I'm just saying it might not be as efficient at small scale when you have like a lot of small pipelines running. And so we decided to build a sort of a V2 version of the platform. We really wanted to focus on efficiency and basically find a way to perform the same type of workload, streaming data, primarily moving from different data sources into different like databases and destinations. And when I started to look into different technologies, this was actually a few years ago, so the project started a while ago. The rewrite big data in Rust kind of thing was getting popular, so I started looking into Rust over DataFusion, and I decided, okay, let's take DataFusion, let's try to make it a streaming engine and see how far it can go. And so today I want to kind of share some of these lessons. And just to keep your attention, here are a few numbers from Gold Sky's announcement post about this a few months ago. In one of the benchmarks, the CPU usage fell from like 10 plus cores to 0.3 cores for like one specific workload. On average, it's probably not as drastic, but you still easily can see like 5x difference. And that translated into cost savings. So because you have like a lot of these relatively small pipelines running in parallel, by moving a lot of them into Streamling, Gold Sky was able to save a lot. And because Flink is a big distributed system, it takes a while to start, so at least like a minute, maybe two. But with Streamling, you can start with just a few seconds. It's super snappy, and this also helps with developer experience. Now, how do you turn a batch query engine like DataFusion into a streaming engine? And a quick data streaming 101 for you. So there are different ways how you can process data. In classic batch processing, you generally have a set of bounded sources. You consume them once, you compute a result, you emit the result, the query is terminated. In a streaming fashion, you have at least one unbounded source. So you keep processing data and you periodically emitting results. So continuously, there's a steady stream of results. Now, if you zoom in a little bit more into stream processing, I generally like to divide it into stateless and stateful. So in case of stateless, you can perform different types of computations that do not require any state between input records. So if you think about functional programming operations like mapping and filtering, generally deterministic for every single input, you can always calculate the output. If you have a join or aggregation, that is typically a stateful computation because the result of that is dictated not by just input record, but also potentially some state. So for example, if you're computing an aggregation, you may store a current counter in your intermediate state, and you need to look up that state in your transformation. Now, going back to DataFusion, one thing I immediately realized at the execution layer, the execution plan operator has the sendable record batch stream type as an output. And if you remove all this Rust syntactic sugar, in the end, this is just a stream of arrow record batches, which looked extremely promising, right? Because there's already a form of a stream here. So maybe it's actually not a crazy idea to turn this into a streaming system, right? So the fact that DataFusion is streaming results between different physical operators is definitely helpful. Now, the idea was, can we implement, let's just start with stateless pipeline first, right? So can we replace some of these components with DataFusion components, right? So for example, in terms of connectors, source and sink connectors, can we just use the existing table providers? And then for transformations, potentially use the physical runtime that execution offers. And then instead of passing a single record at a time, we're just passing arrow record batches, right? That was the idea. And two big questions we had. First, can we reuse the same DataFusion operators, like built-in operators that already exist? Because if we can, then we can save a lot of time, a lot of implementation effort. And the second question you might ask, is this a good idea to use columnar data for a streaming engine? Because historically, engines like Kafka or Flink, they are sort of record at the time system. So we're doing row-based processing. Is it beneficial to go through columns? And I actually think it's a great idea. First of all, you get decent performance because of vectorization, CPU cache locality. Like we know all the good things about columnar data. But most importantly, you can actually control and you can sort of tune the relation between the batch size, the throughput you need, and the latency you need. So I like to quote Micah, who's the creator of a tool called Arroyo, which is another data streaming framework. If you need to fill 100 records in a batch at 1,000 record per second rate, you just need 100 milliseconds to fill that batch, right? And in practice, I'm sure a lot of people here work with much bigger scale. So filling batches quickly is not generally a problem. And if your throughput is very low, then you probably are okay with like higher latency, slightly higher latency for that. So latency is definitely not a problem when you structure data using columnar formats. And in the end, even those classic big data tools like Kafka, like Flink, they have batching already. Like Kafka is not sending a single record at a time over the wire. So there's batching all over the place. It's mostly hidden from the user, so you're not operating on batches logically, but it is there. So coming back to DataFusion, we started with creating our Kafka source. So using the table provider interface, we created a new Kafka source. So in this execute function, we have a Kafka consumer. So it starts, subscribes to a topic, and then starts reading data and emitting data continuously. So the important part here is that it never stops, and it just emits those batches, and we can generate those batches based on the configuration that we have. So for example, I think by default, we're generating about 1,000 record batches at the source. And it's important to mark this as incremental and unbounded. So these are important properties, and I'll mention them in a second again. And so this was our prototype, and well, surprisingly, it worked more or less. At least a few simple queries we started running, and yeah, things look great. So very promising. Next step, we decided to look into how do we scale this, right? Because as you know, DataFusion is a single node system. So if we want to run multiple instances, I know there are projects like Ballista, which again I'm going to mention in a second, but we wanted to find something much simpler. And a lot of the data sources that we had at the time, they were just Kafka topics. And so you can actually leverage Kafka protocol for doing this sort of partition orchestration for you. So if you spin up 3 instances and they all join the same Kafka consumer group, Kafka consumer protocol will distribute the partitions equally across those instances. And so even if you kind of add or remove things. It will rebalance things nicely. And so as long as the computation that you perform is independent, it can be executed in parallel without any kind of shuffles or exchanges, you can scale the system this way, which was really nice because it's a very cheap way to take DataFusion and convert it into a kind of a distributed system. Not truly distributed, but it gets what you need. So scaling out was the concern. Now we quickly realized that unfortunately we cannot reuse a lot of built-in operators in DataFusion, primarily because of the submission type property, right? So if you really think about this, a lot of operations like joins or aggregations or sorting here, they cannot, or they by default are not designed to be incremental, right? So a typical hash join waits for all the inputs to arrive, so it then calculates the final result and emits it. And so when you try to run a join aggregation with a setup, with the Kafka source that's unbounded, you essentially just waiting forever because data never stops, the inputs never end, and so you won't be able to get this final result. So what do you need to do if you want to support things like joins and aggregations in a streaming engine like this? So first of all, you do need that multi-node support so you can perform shuffles or exchanges because for join aggregation, that's kind of really important. And so you can use Ballista. I think there was a DataFusion Ray project, which is now deprecated, if I'm not mistaken. There's also a really promising DataFusion distributed by Datadog. So there are some options here. And I think last time we had a presenter talking about Ballista. It's great to know that this is still going strong. So you need that. Then you also need to re-implement some of these operators. So you need to turn a standard join into incremental join, either by introducing a notion of event time windowing, so you kind of slice your inputs into windows, or even something as simple as just emitting data every 10 seconds. So essentially relying on processing time. You can do some of this. I know some projects kind of follow that path. And finally, also need a persistent state backend support because in case of a streaming source like Kafka, the topic may have retention. And so if your DataFusion node crashes, if it is restarted and you lose that in memory state, you need to find a way to kind of reprocess data from scratch. And so in case of Kafka, it may not be possible. So you want to store this intermediate result somewhere. So you need that persistent state support. And after talking to our customers, after looking through a bunch of use cases, we realized, well, actually, we're not gonna do this for now because a lot of use cases were stateless. So customers were happy with just like stateless operations. And then for a few use cases where you needed to perform, for example, a lookup join, we found creative ways to do it differently, to not require a shuffle. So kind of offload this logic somewhere else. But we do have a stateful backend support. Right now, we just support Postgres because we are not dealing with large volumes of data because it's mostly stateless systems. So we store things like, Kafka consumer offsets in state. But it is available. And potentially, I see a way where we start introducing the multi-node support, and we introduce shuffles, and we build some of these operators, perhaps with windowing. So that might arrive sometime this year. Now, you still have a concern, like even if you don't use something like Ballista and you rely on Kafka consumers, you still need to guarantee reliability. And so imagine a scenario where you're running this pipeline, you're writing data to Postgres, and Postgres goes down. And so you have this kind of in-flight write, which you keep retrying. And then imagine that instance that keeps retrying data also crashes, or maybe it's restarted, redeployed, whatever. You need to find a way to go back and reprocess some of the data that you haven't yet written, right? So you need to have at least once delivery. And in order to do that, we decided to build what's called Shandy-Lamport style checkpointing. So I'm not going to be able to talk a lot about this because I have very limited time, but a very, very high level overview. You have a few different control messages that travel through the system, like these 3 messages here on the right. And it kind of reminds me of a two-phase commit protocol where in the first phase, you ensure that these markers kind of flow through the system. And then the second phase is where you commit the data, potentially write it to your state backend or commit it to Kafka. So this is kind of what it looks like, but I'm just gonna skip it. And I want to mention a few important things. Like if you build a system like this, where you have those control messages that travel through the topology, first, you really want to make sure they travel with the arrow batches together. So you don't create some kind of side channel and you like asynchronously send them, because they will potentially overtake data. You will have all kinds of ordering issues. And so we needed to find a way to essentially embed them into arrow record batches. And if you do that, it also means that the batches must continuously flow through the system. Even if you don't have any input data to process, you need to emit an empty batch because it potentially can carry those control messages. And that also means that all the transformations in the middle, they must propagate those messages, right? So you can keep this cycle going. And so a very simple trick that we used, which is, maybe a hack, but we really didn't have any choice if we decided to stick to the standard DataFusion interfaces, is using schema metadata. So every record batch has a schema, and every arrow schema has a metadata field. So in case you didn't know. And so metadata allows you to essentially attach any kind of random piece of data you want. And so we take our control messages that need to belong to a certain batch, and we just encode them in JSON and store them in metadata. And so if there is a transformation that then needs to propagate this downstream, it will simply copy the metadata from the input batch into the output batch. Kind of hacky way to do this, but it works, and we're happy with it so far. So now we have our Kafka source. We have the at least once delivery figured out. We know how to scale things. We are not targeting join segregations. Surely simple stateless workloads should work now, right? Like, what else? What else, dude? And think about a simple like filter or projection. I just want to make sure that works. And we still had some interesting challenges with DataFusion. So I want to talk about the first one in the middle here. For projections and filters to work, as I mentioned, we want to make sure the batches, even empty batches, they still flow through the system. And for example, if you check the standard filter exec operator in DataFusion, it has an optimization where if the output batch is empty, the operator does not emit the batch, because in a batch query system, it doesn't make much sense. Like, why would you emit an empty batch? So it still just waits for the next one, the next input. And we had to essentially patch that operator to emit the batch anyway, even if it's empty. And for that, you can actually leverage physical optimizer. It's quite nice. So you just search, do I have any filter exec operators in my topology? If yes, replace them with the streaming filter exec, which was that customized version. And so this part was fairly straightforward. Another interesting thing we discovered, DataFusion has a lot of UDFs, as you probably know, and some of the UDFs have a stable type, what's called. And so I'm going to read this snippet over here very quickly on the left. A stable function may return different values giving the same input across different queries, but must return the same value for a given input within a query. And so this is typically applies to current time, current date now, so those kind of functions. And so if you try to running it in a streaming system, you will see something like this, where you have your now call in the query, and you look at the results and you realize that all of the results have the same timestamp. And it's because by default, it tries to just compute that result once and then cache it. And then you will see data that's exactly the same during the duration of the query. So this optimization makes sense in a batch world, but in a streaming world, I only have one query, it never stops. So we actually had to re-implement these as volatile functions and override the built-ins. So this was successful. Another interesting thing we had to face query engines like DataFusion, they love optimizations. They love, projection, predicate, push down. But these optimizations typically don't make sense when you use something like a streaming source like Kafka. And so imagine that you have this type of pipeline where you have multiple downstream transformations, and excuse me, and you potentially use different projections, different filters. And so you want the data to be scanned just once on the Kafka side, but what DataFusion does, if you try to kind of define that, it will spin up several sub topologies, and each of them will consume the same data from Kafka source again. This makes sense if you're querying like Parquet data, like iceberg table, but in case of Kafka, you really just want to consume it once. And so this is probably similar to the question from Milind about multiple downstream nodes. So we actually had to build a way to detect this and inject a node in the middle between Kafka source and this downstream transformations. And that node broadcasts the results to all of these downstream children. Maybe it's slightly different that you asked about, but yeah, kind of similar concept. So you kind of detect these situations where you have like multiple consumers, and you tweak your logical plan to introduce this broadcasting feature, and you kind of stream the results and consume them only once. So these are some of the interesting kind of challenges that we faced. And I also want to mention our plugin system, which I think is a very interesting selling point for our users. So with our plugin system, you can basically implement a source transformation sync, like all of these different components, simply by implementing this very high-level interface you can see on the right. So primarily this process batch function. And it's based, as you can guess, on FFI and ABI stable crate. And we ensure that there is zero copy record batch passing. So the data goes to the plugin, then comes back from the plugin in a zero copy fashion. And once you build this plugin, you can dynamically load it in runtime, and runtime takes care of all the validation, back pressure, checkpoint, like all of those concerns. And so a lot of internal and external users have been fairly successful with building these plugins very, very quickly, and then just loading them into the runtime. I think I have a few more minutes left. So I just want to very briefly mention this another interesting thing we built. A lot of people wanted to actually write an imperative language, not SQL, in transformations. So we integrated DataFusion with WebAssembly. So you can create a TypeScript to JavaScript function that can process data. And so the input here would be an error record batch. Yeah, I'm just going to skip these details. But the interesting thing is we're trying really hard to minimize data copying, but unfortunately with WebAssembly, it's really hard. But at least like on one direction, we found a way to read arrow data without copying it. So yeah, it's interesting that even though we can't fully leverage arrow like end-to-end here, there's already some libraries, I believe it's called Flechette, that allows you to read arrow data from JavaScript. So this allowed us to have this relatively performant WebAssembly transformation. Yeah, I believe I am over time. So just to quickly summarize, I personally believe that a lot of the data-intensive applications nowadays should just default to arrow or any columnar formats. So including streaming, analytics, right? Unless it's OLTP, yeah, stick to arrow. I think it's a perfectly safe choice. And using something like DataFusion allowed us to build this, in a few months instead of years. So highly recommend. And yeah, if you are dealing with streaming semantics, they can offer some really unique challenges, but there are workarounds, and they're really fun to solve. Thank you for listening. And if you want to check the project, here on the right, you can see the QR code and the link. It's streamling.dev, very easy to install. And yeah, happy to hear your feedback.